Thank you for coming to Software Architect for the Intel open source 3D graphics driver and Intel representative Chronox. Please welcome Ian Romanick from Intel.
Hi, my name's Ian Romanick, and I very much apologize for the unusual slide title. That wasn't intended to be the title of the presentation, but things happen. So what I'm actually going to talk about is Intel's open source driver for integrated graphics parts and how you can tune your applications for that driver stack on that hardware for general Linux and for SteamOS. So first I'm going to talk a little bit about why you should care about Intel graphics, give sort of a brief overview of the Intel Gen graphics architecture, give some general optimization tips, and then talk about a bit about some tools that we have both integrated directly into the driver stack and as external tools that you can use to kind of help you along the way. There was a time when Intel graphics was a checkbox that you had to have integrated graphics so that you could do word processing and Office kind of applications. But then somebody decided, hey, we can actually do some really cool stuff with this. So over the last few years, the hardware teams, as hardware teams do at Intel, set some really, really aggressive goals for themselves. They said, we want to make stuff that is fast. And over the last few generations, we've seen a very tremendous ramp up in the performance of Intel parts. If you go back as far as Sandy Bridge and even some of the earlier parts and compare the performance from generation to generation, the increase is pretty astounding. Each time when we get a new graphics part that we have to start supporting, the first thing that we do when we get real production parts instead of the alpha silicon, so we start poking at the performance, and it always shocks us. And we've been doing this stuff for quite a while. So looking at a particular example that you'll get to look at quite a bit more closely later, and hopefully I won't delay you from getting your new toy, is the Gigabyte BRIX Pro that has basically our top-of-the-line CPU with the top-of-the-line GPU. That includes all the hotness that you would expect in a high-end PC and integrated graphics with 128 megs of EDRAM. And it's really that giant pile of EDRAM that makes this part really, really fast. So if you compare this system with a bunch of other systems that you might find in the living room, not only is its performance really good, but it's freaking small. I mean, it's smaller than a Wii. And no one has ever confused, that high performance has never been the target for the Wii. It's been targeted at small, and we're smaller than it. So in terms of open source on Intel graphics, we've been doing this for quite a while. We've had a team at Intel very actively supporting open source since around 2006. We have an open source OpenGL driver that we actively maintain. We also work quite heavily on the X server in the kernel, on other technologies like Wayland, and we have a pretty decent sized team that spans over quite a broad area from North America and Europe and Asia and Zealandia, which is actually the continent of New Zealand, believe it or not. We sometimes joke that the sun never sets on our graphics empire, but that's just because we have some people up in Finland, and in June the sun doesn't set there. And we're not just, this is an open source project, but this isn't just a bunch of random yahoos on the internet who do some stuff for a while because it's fun and then they wander off. I've been actively working personally on OpenGL drivers for Linux in open source since 2001, and a bunch of the other people on the team have been around a similar kind of time frame. So we've been at this for quite a while, and we're dedicated. It's a labor of love, if you will. So what we currently support on our graphics chips is OpenGL ES 3.0 on Sandy Bridge, Ivy Bridge, and Haswell. We're planning support for the next version of OpenGL ES, at least on Haswell Other parts will get support as we have time and customer demand. Right now on Ivy Bridge and Haswell, we support OpenGL 3.3 and a big pile of extensions. If folks are interested in knowing exactly what the set of extensions is that we have, I'd love to chat. We only support the core profile. We set some pretty aggressive schedules for ourselves, and one of the choices that we made to be able to aggressively get performance and quality and ship things fast is we had to cut the compatibility profile, and it should die in a fire anyway. We support a variety of variety of texture compression formats. Right now we support S3TC like everyone, although we don't advertise the X texture compression S3TC because exposing that extension requires that we have a compressor so that you can give uncompressed data to the driver. Raise your hand if you give uncompressed data to the driver and want the driver to compress it. 2 guys. Okay. Rich Geldrich has a really nice library you should use instead. So we don't expose this extension because of the patents, and that ends up being problematic putting that in the open source project. So support for pre-compressed textures is fully there. In ES contexts, we also support ETC1 and ETC2 on Bay Trail, and Bay Trail is the only shipping part that we support ETC on in desktop contexts, and also just for lulz, we support FXT1. I'm surprised that they haven't cut that out of the hardware. Raise your hand if you use FXT1. Even less than the people who want the driver to compress their data for them. Our hardware architecture is in kind of an unusual middle land between the variety of other hardware architectures that exist. So on the one hand, we have a unified memory architecture like most mobile parts. But on the other hand, we're not a tiled renderer like most desktop parts. So we have a whole bunch of the usual sorts of hardware optimizations for non-tiled renderers that you expect from a desktop part while still being UMA. We also have unified shader execution units for the most part. The other unique thing that we have is a really, really large last level cache that's shared by the CPU and the GPU. So one of the problems that people frequently have with discrete cards is if you want to read stuff back from the GPU, it takes forever. And transferring data from, in either direction is more painful than you want it to be. And having this large cache that's shared by both units and that both sides can snoop makes things really performant. So we have kind of a block diagram of a bunch of the parts of our architecture, command streamer, the execution units, memory, and the different programmable stages. So one of the more unusual things that we have is this URB at the top, which is the Unified Return Buffer. It's a region of on-chip memory that's used to share data as it gets transferred between the stages. So I'm going to walk through this a little bit. So the vertex fetcher is going to pull data from memory and dump it into the URB. Then when vertex shader threads get kicked off, it's going to pull data from the URB and dump it into registers in the execution units. And then when the vertex shader is done, the previous data in the URB gets overwritten with the vertex shader outputs that are then going to go through a similar process to go in and out of the geometry shader. And the clipper is going to pull the data out of the URB. And then the URB kind of drops out of the picture at this point as data goes through some sort of specialized FIFOs between the clipper, the strips and fans unit, and then down into the fragment shader that's going to write data out to the color calculator that does the blending operations through the frame buffer and all the sort of back-end per fragment operations. So most data that gets into the execution units comes through the URB. So all of the non-UBO type uniforms go through the URB, vertex geometry and tessellation inputs, And all of this data gets pushed into execution unit registers when the shader thread gets dispatched. So if you ever go looking through our hardware documentation, and there's a link a little bit later, or looking at the driver code, we'll make a distinction between push and pull constants. So the data that sort of magically shows up in registers that comes through the URB is the push data, because it gets kind of shoved in. And then other things that get fetched other ways are the pull. So other sorts of data, textures, text bows, and UBOs all come through the sampler. Also, some non-UBO uniforms can spill out into sort of hidden behind-the-scenes UBOs if you have a lot of uniforms, or if you have some arrays that have non-constant indices. So the shader execution cores are unified, but they execute in a couple of different modes. So the vertex shader executes in array of structures mode, and 2 vertices get dispatched at a time. The fragment shader operates in structure of arrays mode, and depending on register pressure, either 8 or 16 fragments will get dispatched at a time, and then some fairly common sorts of channel masking techniques are used for per fragment flow control, and for pixel discards, and for masking around of pixels that aren't lit around the edges of polygons. So I'm going to come back to how some of this stuff affects you a little bit later. So all of our hardware documentation is publicly available. You can go to these links right now and download documents for our chips back quite a number of generations, and I believe that the documentation for Haswell GPUs was just posted fairly recently. All of our driver source code is also available. The first link there is a landing page that shows where to get access to all of the various different code bases, the kernel driver, the user mode driver, the 2D driver, and a couple of other related things. And there's some instructions about building it. The last link is just a direct link to the Git repository for the user mode part of the 3D driver. All right, so now we've gone through a bunch of the sort of background stuff. Let's talk about some of the details and get into some, how this affects you and how to optimize for this kind of architecture. So the first thing is make sure that all of your data that you want the GPU to use is in a buffer object. Think of buffer data as your malloc for everything that's going to the GPU. And you can use map buffer and preferably map buffer range to get direct CPU access to that data. And because this is a UMA with a giant shared cache, using either of the mapping commands will generally give you direct access to the actual buffer that the GPU is going to use. So there's none of this copying data around or giving access to some on-card memory that's very slow to access from the CPU. You're just getting regular old cached memory access. So use map buffer range for asynchronous mappings, and use multiple BOs to avoid the synchronization when you wrap around the buffer if you're using a large buffer to stream in, for example, vertex data. Or you can also use GL buffer data to orphan the storage. So when you get to the end of the buffer, just call GL buffer data with the same size, and the old buffer will get orphaned and released when the GPU is done accessing it, and you get fresh storage without blocking. Avoid using staging buffers where you write into a buffer and then use copy buffer subdata or something to transfer from one buffer to the other, and avoid buffer subdata. In essence, buffer subdata is effectively a CPU allocated staging buffer. On the fragment shader side, we dispatch at least a pair of 2x2 subspans at a time. So it's the fairly common, dispatch for a quad of pixels at a time so that you can calculate derivatives. Uniform flow control across any of the pixels in the 8-pixel group is cheap. Non-uniform flow control within the 8-pixel group is more expensive because you have to execute generally both branches of the if statement and throw away a bunch of the values that were calculated. In addition, we have a mode where we can dispatch a pair of these 8 fragment groups to dispatch 16 fragments at a time. What effectively happens is each instruction in the shader gets fetched once, but then it gets pumped through the hardware twice. I think that the docs sort of euphemistically call this instruction compression, which I always thought was a fairly bizarre term for this, but it's really double execution of the same instruction with a different set of data. Everyone has some sort of post-processing filters in their games. Raise your hand if you have some sort of post-processing in your game. Okay. Well, maybe not everyone, but just about everyone. So the simple box filter. And it's surprising how often we see people sort of noob their implementations of these kinds of post-processing effects. So if you want to do this fast, use textureOffset, and there's a number of related functions to fetch a group of pixels in a small neighborhood. This is going to use less instructions, less registers, and less URB space. Do not do either of the techniques on the right where you have some set of offsets that you pass in as uniforms that happen to be the texel coordinate delta to be off by a pixel, or pass in absolute centers as shader inputs of different coordinates. Both of these will generate piles of instructions that you don't want and will make your code go slower. And both of these techniques, or all of the texture offset and related functions, have been around for a really long time. So it still surprises me when I see new apps pop up on Steam that still do that kind of thing. We usually, like, what are you doing, guys? So simple instructions, and the definition of simple seems to grow for hardware generation to hardware generation, have a latency of 14 cycles, and this has recently grown to include reciprocal, exponents, logs, and a bunch of the other instructions that, in days gone by were the expensive ones that you wanted to avoid. The only one that's still expensive is PAL, that has a 22 cycle latency. Texture accesses are on the order of 140 cycles if you hit the cache, and 700-ish if you don't. The issue rate is still around 18 cycles, but you've got a lag before the data shows up. And these are the values that our instructions scheduler and our compiler uses for Haswell. The times are a little bit different for previous generations, and on previous generations, the complex math instructions had longer latency. So another technique is to use compact varying, so only use as much varying data as you need. So if you know that you're always going to pass 0 and 1, don't pass that. Make your vertex shader output only a vec2, because we will instead of passing all of our data in sort of a vec4 centric manner, we'll compact things down and use as few individual slots as possible. So in addition, Intel GPUs don't have fixed function interpolation hardware. So at the beginning of the fragment shader, we'll actually emit instructions that perform the interpolation. So if you send just constant values of 0 and 1 over like that, not only does it do some extra work on the vertex shader side, but then on the fragment shader side, it's going to try and interpolate those 0s and 1s. If you never actually use the Z and W components of that, it'll end up getting dead code eliminated. But if you do a dot product that you expect to have the 0 and 1 behave as 0 and 1 in that dot product, they'll still be used, and it'll generate all those instructions. So if you have per primitive data, declare that varying as flat. So if you know that you're going to generate the same value for a particular varying in all the vertices of a triangle, declare it as flat, and then we won't generate any of those interpolation instructions. So the compiler is going to do compaction of variants, pardon me. So you don't have to sort of manually pack things. And in fact, doing a bunch of this manual packing has a tendency to trick our register allocator on the vertex shader into thinking that some of the life intervals are larger than they should be. So just write the natural code. If you've got a vec2 and a float, declare them as a vec2 and a float. Don't try to stuff them into a vec3 thinking that you're being clever. You're just doing more work for yourself. All right, so we've talked about a few kind of general optimization techniques. We can look at a bunch of tools that we have to sort of help you out a bit along the way. Most of these are actually built directly into the driver, and some of the debugging techniques are sort of directly come from the architecture of the driver. So we have a number of environment variables that you can use to control things, control output that the driver is going to create. A lot of this is also actually available through either the ARB debug output extension or the KHR debug output extension. I believe that we currently only have KHR debug wired up in desktop OpenGL context, that it's not yet wired up for ES contexts, but that should be trivial enough to change. So there's a few sort of driver-specific controls that we have that are controlled through the Intel debug environment variable, and you can also get some output from the sort of higher level compiler used through the Mesa GLSL environment variable. The most useful of them is the dump value, where it's going to emit all of the shaders that come in through the compiler. So one of the most useful of the Intel debug settings is the perf setting, which is going to cause the driver to emit a bunch of warnings when things have happened that makes it fall off optimal paths. So if you hit a case where it has to block to do a buffer mapping, or has to block on to wait for an occlusion query result, or if it's going to do a state-based shader recompile is the big one that people really like to be able to track down, or if there are cases where you've missed 16-wide fragment shader execution. And I think the last time when I audited the driver, there was about 70 of these different warnings that it will give. And all these are also available through our debug output. So if your application is already set up to get performance warnings through ARB debug, you're automatically going to get these. This just makes it get dumped to standard output. So in addition, you can view the assembly output for vertex shaders or fragment shaders, and you can combine these. So if you say Intel debug equals vs, fs, perf, you'll get all of it. You'll get the assembly of the vertex shaders, the fragment shaders, and all the perf warnings. The one slightly tricky bit about this is that it also dumps shaders that are occasionally generated internally by the compiler. So there's a couple of cases. I think there's just a few cases left where internally we'll actually generate a GLSL shader to do like blit frame buffer kinds of operations, and those will get dumped out too. So every now and then you'll see some shader and think, that is not from my code. And you're totally right, it's not from your code, it's from ours. So what one of these dumps looks like, and I really apologize for the eye chart. You people in the back are really getting the short end of the deal on this. So up at the top is the internal representation that the higher level compiler uses to represent things. It's sort of a scheme-like language that's fairly ugly to look at, but it matches the representation of the compiler. And then below is the actual assembly dump that is going to get sent to the GPU. Now the thing about this that's most interesting is this little bit right here. So this is a vertex shader that's going to execute in vec4 mode. And the scheduler has estimated that this shader is going to take 44 cycles to execute. The trick about this is flow control will often really confuse this, and so you'll have some big complex shader and it'll say this is going to take 16 cycles, and it's a lie because it just got confused by the flow control. But for straight through code, it's pretty much always spot on. So we can see similar for the fragment shader, and in the fragment shader case, we actually get two dumps of this simple shader. One is for 8 wide and the other is for 16 wide. We have to send both down to the hardware, and the hardware will pick cases where it wants to dispatch 16 fragments at a time or 8 fragments at a time, and it's black magic. And again, we get an estimate that the 8 wide is going to take 22 cycles and the 16 wide is going to take 30 cycles. It takes longer, but you get twice as many fragments out of it at a time. So the place where there's two places where this is really useful. One is the cycle estimates, and then the other is that you can look at these dumps, and if you've missed 16 wide, so in order for it to execute in 16 wide, what it effectively does is when the instruction gets executed once, it operates on the top half of the register space, and then when it gets executed again, it operates on the bottom half of the register space. So effectively, in 16 wide, you have half as many registers. So if you have a really big complex shader that has really high register pressure, it just won't be able to generate it for 16 wide without having to spill to external storage, and that's always loss. So you can look at this output and kind of get a fat thumb estimate of, oh, I'm using this many registers. I'm actually pretty close to being able to get this to be able to fit into 16 wide. Maybe I can tweak things or cut some things out of it and be able to get 16 wide. And we use this a lot when we're looking at shaders that we get to see if we can come up with additional optimizations in the compiler so that we can get the register pressure down a little bit so that we can get the shaders to fit into 16 wide. So another control that we have is called shader time, where it's going to actually do the old read timestamp counter trick in the shaders and collect up all that data, and as the application is live running, dump out data about which shaders are taking what amounts of time. So we have a capture of this for a sample application that I wrote where it's dumping out where each individual shader is taking approximately so much time, so you can get an estimate of which shaders are taking the most time, and then use that to guide where you're going to spend your optimization efforts. And we do the same, right? We will run applications through this and say, this shader is the one that's taking all the time, and then correlate these shader IDs. In this case, this particular application only actually has one shader that it's using. And if there's time at the end, and I think there will be, I'll show it live. You can correlate these IDs with the numbers that are on the output of from the dump. So this is the code for shader 0, and in this output it's talking about shader 3. So you can use those to figure out which shader it actually is and kind of work them together. So another nice thing that you can do with the open source driver is it's really helpful for debugging GL errors. So you can already use the various debug output extensions to get information about when a GL error has occurred, which is definitely better than having to sprinkle GL get error all over in your code like we used to have to do in the old days. But if your app isn't already instrumented for debug output, it still means you have to go in and write a bunch of code and do some instrumentation. So alternately, you can say Mesa debug equals verbose, and it will just dump out whenever a GL error gets generated by the application. And also, you can just set a breakpoint in the function in the driver that emits that message. So you can launch your application in the debugger, set a breakpoint at Mesa error, and run it, and as soon as an error gets generated, it will stop, and you can just walk back up through the backtrace and go directly into your code and try to figure out why the heck an error got generated. you've also got the code right there, so you can look at the code in the driver of why exactly it thinks the data that you gave it was worthy of generating an error. And that can be really useful. You can do similar techniques for frame buffer attachment incompleteness, which is a frequent source of irritation by setting breakpoints at FBO incomplete and attachment incomplete. You can also set a breakpoint at any GL function. So if you know that somewhere in your code you're calling GL buffer subdata and you don't think that you should, you can just set a breakpoint at _mesa_ buffer subdata, and as soon as you call that, you'll hit a breakpoint right there in the driver, and then you can look back up through your code to figure out how you got there. So, and here's an example of doing that, just setting a breakpoint at Mesa error, and then it stops down in the driver code, and then you can walk back up through the backtrace to see what happened, which actually I think the next slide shows. So frequently when people are benchmarking code, you want to, if you've made something that you believe is an optimization in your code, you want to do before and after tests, but GPUs like to change their clocks around and adapt things, and that can make it hard to get consistent data for your before and after checks. So one thing that we frequently do is, if you want to do a bunch of before and after checks, is lock the GPU at a particular clock speed so that you're going to get consistent clocks. So in sysclass DRM card 0, there's a number of files in there that control the frequency of the GPU. So GT min frequency and GT max frequency bracket the range of possible frequencies, and then curve frequency is whatever the frequency is right now. So if you want to lock the GPU at the maximum frequency for before and after testing, you can just echo, in this case, echo 1250 to GT min frequency, and since min frequency and max frequency are the same, there's only one possible value in that range. So you can lock it, by setting those values, you can lock it at any particular point. So if you want to see how your app would, if you have a desktop part and you want to kind of get an estimate of how your app would run on a lower clocked mobile part, you can use that to also lock the GPU ranges to get some kind of estimates. So one of the other debug tools that we have that I think Rich stole most of the thunder about this a couple of rooms over earlier is API Trace, that lets you collect traces of running GL applications and then replay them later on different systems and be able to trim the traces and inspect GL state and do a bunch of things. This is useful for both debugging applications and seeing what's happening in the applications, and it's also really useful for reproducing driver bugs. If you found a case where on one particular card it doesn't render right, you can capture a trace and trim it down and then send that trace to the vendor and say, you're doing this wrong. And then they can like concretely see, oh, okay, so we're getting that result and try to figure out what's going on, and you don't have to worry about sending them your giant 4 GB game that you haven't released yet. So another tool that we have that's in a fairly early state is called FIPS. It's kind of a cousin of API Trace. Instead of collecting the actual trace of the GL calls made by the application, it collects a variety of performance metrics as the application is running live, and squirrels them away in a file for later inspection, or you can view the graphs live. So you get a variety of graphs. So one of the sets of things that you can get out of it is comparing CPU load, and it looks like we got rid of the GPU load graph off of this one, but the amount of time per frame. The sort of unfortunate thing about it right now in its current early state is that it's collecting a whole bunch of data regardless of what data you actually want to be able to inspect later, so it does add quite a bit of overhead. I think I don't recall what we figured out last night was the frame rate dip that we were seeing, but it's it's still pretty substantial, but it can, even in this early state, you can still get quite a bit of good information out of it. And we're working on improving the performance counter data that comes out of the driver that this application uses, and we're hoping to get that wired into Voggle and a couple other introspection tools here in the near future. So you can also just use your favorite CPU profiler. If you want to find out where your CPU time is going, the driver isn't some magic black box. You can see exactly where in the driver time is going. And that can tell you, one of two things. Either you're not using the GL API in a way that's particularly friendly for the driver, and maybe there's changes that you can make, or maybe there's just something suboptimal that we're doing, and you can send us a bug and say, this part of your driver is too slow. But you have, so this is the output of sysprof, and you can see all the way down into the lowest levels of the driver. This is actual data out of Xonotic. You can see all the way down where it's spending time, that it's not just, oh, it disappeared into some function in the driver with some obtuse name that means nothing, and then I have no idea where it went. Our development team is also very accessible. We're regularly on IRC and are around to chat. Because we do have people all over the planet and people who keep really, really weird hours. It's hard to find a time when there isn't someone available to talk. We also have a mailing list, an open mailing list where you can ask questions about what's going on in the driver development. There is a public bug tracker. There's a fairly detailed page about how to submit good bugs that we'll be able to respond to and take action on. And we are also hiring. So if you or someone you know has interest in doing driver development, please contact us. Unfortunately, I can't offer an awesome bounty like every game on Steam, but we'll be your friend. How about that? Okay. Any questions?
You might have mentioned this, but when do you expect to have OpenGL 4.0 support running on Linux?
We don't currently have an ETA. Right now, we're actually more focused on the next version of OpenGL ES. And a big part of our efforts, you may have seen that there was a small announcement on Chronos about some of the functionality that's in that. So actually, the thing that we're looking at next is compute shaders, which actually reminds me, could I see a show of hands of who is interested in tessellation shaders? Okay, and who is interested in compute shaders? So it looks like maybe slightly more for compute shaders. Okay, previously when I've asked that question, there's been the one guy in the back that's like, yeah, I want tessellation, and then everyone else is like, no, I hate tessellation, I want compute shaders. So that's actually where we're focused next. There's quite a bit of the 4.0 functionality that we already support through extensions. I think the only things that we're missing, I believe there's 3 things that we're missing: tessellation shaders, shader subroutine, and double precision. And we've basically been prioritizing the order that we do work by developer demand. So it's seeming like there's been more demand here for tessellation than what we've previously heard. So we may reevaluate things, but it's still big piles of work.
And one follow-up, do you guys support multi-sample textures right now?
Yes.
Great.
Yes. At least on Ivy Bridge and Haswell. I don't remember about Sandy Bridge. Yes, on Sandy Bridge. Okay. About a big chunk of my team is here with me. So.
Do you have any plans to support OpenCL acceleration on the GPU core?
So I believe that there is a team at Intel working on it, but it's completely outside the scope of my team. But we are working on compute shaders, so I don't know if that fills the need that you have, the compute need that you have. Okay. Yes.
Do you guys share any resources with the closed driver team?
No. No, it's a completely separate project.
And I just wanted to say,
As one of the members of the driver team, we really would love to meet all of you. And as you're bringing your new games to Linux, we would love to see those work great on our hardware, and we'd love to work with you guys to optimize our driver for your workloads and get in touch if you're seeing any issues or problems. So as Ian said, really get in touch with us. We're here. We'd love to talk to you. And if you don't catch us here, we're online all the time and happy to talk directly to you.
Yes. So when you get home, try your game on the box that we're giving you, and then contact us on IRC and tell us either, yeah, it works great, or we hate you, your stuff sucks. We want to hear either one.
This is semi-off topic, but is it actually physically possible to open source a driver on Windows?
I have no idea.
Okay.
I have no idea. I mean, I would assume that hypothetically you could, but I don't know if it requires, stuff from Microsoft. I don't do Windows. So I did want to show. I did remember one other thing. So here is. Here is a simple demo that's just a bunch of helmets drawn using instancing, running, and then setting the environment variable, the shader time environment variable. It's going to run the same demo. It's going to go a bit slower, but as it's running, it's going to dump out live data about which shaders are using the time. And so this didn't require any instrumentation in the code or using some external app. It was just set an environment variable and run it again. So we can do similar, let's say until debug equals VS, and get the dump of, so this one is a bit, let's do it like this. So this is a bit more complex vertex shader in this. So first it dumps out just the compiler's internal IR, and then it is going to dump out the assembly code with the IR sort of mixed in between, so you can see what the hardware actually sees from your particular shader. And then if we do, it's going to dump out. So then here's the bunch of the actual shader code for the vertex shader. Let me scroll this a little bit. So you can see the GLSL code for the vertex shader and the fragment shader, and then it's also going to dump out the IR that came from those. So there are some fairly primitive utilities that are built directly into the driver to do some introspection into the application. It's sort of a good, easy first thing to check and poke at when you're starting to look at how an application is running. All right, thanks.